Well, welcome back, everyone. Looks like we can get started. We're now in week number 11. This is actually kind of a pivotal week for us for lots of different reasons. But one thing I want to mention is spring break is wonderful, except that it's extremely disruptive when you think about it. We were in a pretty good routine on just doing ordinary classroom work, doing lectures. If we spend an entire week falling off that routine, it's actually not as easy as you think jumping right back into the schoolwork routine. And now that we're back into it, we've got some pretty pivotal weeks. This entire week right here, we're covering a couple different, majorly different methods. Two means in chapter 18, switching over to categorical data in chapter 19. Next week after that will be about the same. This week is a little bit different. When we're on Thursday of this week right here, we'll take any questions relative to our third exam held on this week. And then that makes this week an exam week. Thursday of this week is an ordinary instructional week, but now the university policy for ISU is getting back into a closed week policy. Where on closed week, we can't actually introduce any new material. This will be a full-on review week for us. Our final exam is a take-home final exam. So the way this works is we'll have a review on Tuesday. When we end our review on Thursday, we'll spend the last 15 minutes to actually assign the final exam as a take-home exam. And it will be due as a 1 week turnaround for Thursday on finals week. So that's the last bit of the plan going forward. So again, what this means is this doesn't actually happen as much in fall semester when you think about it. In fall semester, the Thanksgiving break, you only have like 1 or 2 weeks and then the course is over. So usually people are wrapping things up. But spring semester is touchy. With spring break coming back into our routine of schoolwork, there is a lot of pivotal things that we have to do on these remaining weeks. They are kind of intense. And because we have 2 exams left over, let's take a look at that percentage. With 2 exams left over, that means as far as the course goes, that is 30% of the course still on the table. It is a lot. So you have a lot of opportunities to really improve your grade. This is a really pivotal block of weeks that we're in right now. And anything you can do to get back into that routine of getting through the work, doing the reading, attending the classes is going to make a huge amount of difference at this point in the course right now. But welcome back. It's week number 11. We don't really have too many more weeks when you think about it, looking at what's left over in the Moodle website. But so far, we're about to complete chapter 18. We're on the very last example there. Then we'll be turning over to the categorical data. Well, any questions at the moment, folks, about the plan so far? Okay, well, our goal is to do more statistics. So that's what we're about to do. And the problem we're about to take a look at, it pairs together with the problem that we looked at in chapter 17. So let's refresh that problem here. In chapter 17, we were working with data that was absolutely paired and totally dependent data. When we did this kind of data, because of its dependent nature, we didn't individually analyze the columns of data. We formed the pairwise differences like you did in the corresponding homework assignment for this section. And that means when we did condition checking, we did condition checking just on the differences, nothing else. Now hold those thoughts in the back of your mind because we're about to deal with data that looks like this, but it's fundamentally completely different kind of data. So now we're looking into these data. Let's read through what this is about, then we'll make some comments about it. We looked at this right before going on spring break, but let's just refresh our minds on it. This is about the so-called thematic apperception test. I don't know a lot about it personally, so we're trusting the psychologist that this is a meaningful thing to test people on. We'll refer to it as just the TAT. What it does is present subjects with ambiguous pictures, think maybe ink blots maybe, ask them to tell a story about the picture, and then they rank the stories according to some scoring system that has to be very, very carefully thought about and defined. So it says here they can be scored in several ways. And these folks here asked mothers of 20 normal and 20 schizophrenic children to complete the TAT test It was scored for a number of stories out of 10 that exhibited a positive parent-child relationship. Now, again, that's a pretty big statement right there. Whatever is considered to be a positive parent-child relationship is something that would have had to be informed by experts in child psychology. This is a big part of the study already in itself. So lots going on in this kind of problem. We have normal children. We're not saying normally distributed children. I'm probably just going to say ordinary children so we don't conflate it with a normal distribution. We have children assigned a diagnosis of schizophrenia. And in this column is a number of so-called positive parent-child relationships stories. And same for this column over here. I'll just refer to it again as simply the TAT score for both. So our job here is to see if there's a difference between, but already automatically we can say that we have two independent samples. What makes these samples independent this time is any row you select, any one whatsoever, say this row, the score from this child at 2 points and the score from this child at 1 point have nothing to do with each other whatsoever. But in chapter 17, if we go across this row, those values have a lot to do with each other because they're two measurements made on the same exact patient. That's what made it dependent data. We have independent data this time. Both samples are at size 20, so we have sample sizes going, once I get out of the table, there we go, that was tricky. We have a sample size N1, which is 20 from the ordinary children, and a sample size N2, also 20 from the schizophrenic children. So that's our setup so far. Well, any questions, folks, about the data at the moment? Okay, now we know what we're going to do on this because it's in context. We know we're in chapter 18, but you have to imagine if this was a final exam problem, it's going to be mixed together with a bunch of other problems like this one. It's actually randomized. I randomized once. I'm not going to cherry pick the randomization, so I'll just let RStudio do the randomization for us. But that means this problem would be out of context, more likely than not. And it's this part right here that tells us use the 2 sample T procedures. Whereas in the last problem, the moment we saw dependent data, that's why we used just the 1 sample T procedure. Analyzing the differences was the major idea. Well, we're about ready to start. We want to give a complete analysis to this. They didn't say a lot about how they wanted it to be analyzed. They didn't ask for a particular direction that one might score higher than the other. They left that completely open, which I would agree is appropriate for this kind of problem. So we have to decide all on our own just how to analyze. It does indicate we'll analyze it as a hypothesis test. That's in part A. And then in part B, way down here, we'll provide a follow-up analysis by also providing a confidence interval and interpreting it as well. So starting off in part A, complete analysis with the hypothesis test, we want to start by just saying what is the practical question that deserves a statistical analysis. Any volunteers to say what would be, in your mind, the practical question? A little tougher, right? Because they didn't say much right here. We kind of have to just infer something. There's no statement with a question mark telling you to analyze it this kind of way. So it feels like there's stuff missing here. But if you ever get a problem that looks like this with no direct direction on how to analyze, it is going to be a two-tailed test as a hypothesis test, which means you could say something simply along the lines, is there a difference we have to mention what are we analyzing? It's quantitative data. So we have to say, what is the type of data we're analyzing? It's that TAT score, Thematic Apperception Test score. So we want to know, is there a difference in the TAT score? Now, pausing for a little bit, they gave us some informative information on how this TAT score is measured, positive parent-child relationship, but I'll paraphrase it just by simply saying the TAT score, knowing that it's defined down here as part of the problem. So we want to know, is there a difference in the TAT score between ordinary children, replacing the word normal just for the sake of clarity, and schizophrenic children? That is a harder word to spell than I realized today. So that would be a pretty good way to start. But I feel like if you write down a statement like that, I wouldn't be super critical and take off a point. There really is something missing. If we say it this way, we're talking about individual children, but that's not what we're saying really at all. We're talking in terms of averages. We are meaning the average of all ordinary children, TAT score, versus all schizophrenic children, TAT score. Are those averages different? So we should say here, just to be clear, it'll help us out in our analysis, add on average, some way, shape, or form, even in the practical question, just to keep yourself on the right track for your conclusion. So that in my mind would be a pretty good practical question. Now we have to get going by doing the nuts and bolts of the statistical analysis. Because we're dealing with averages, we actually need to write them down, and they're parameters this time. So we'll use the mu1, mu2, or mu0 for ordinary, mu sub s for schizophrenic, really up to you how you'd like to analyze. For this problem, I'll go let just mu1 and mu2. I'm going to let mu1 take the role of the first column and mu2 take the role of the schizophrenic column, but really up to you how you'd like to define these. So let's say let mu1 and mu2 denote lots of words you could say: population mean, population average, true mean, or true average. Just pick a stylistic choice and be consistent with it. I'll go population mean. Let me put an article in there first. Denote the population mean. We have to say this word if we're analyzing quantitative data, because we're analyzing the averages. We also have to say mean of what specifically. It'll be the mean TAT score. So that part has to be in there to say what is the nature of the data. And then we have to mention the populations as well. We kind of indicate them here and here in the practical question. So we'll say mean TAT score for ordinary and I'm really sure I'm not spelling that correctly. Let me take a quick peek at that. Okay. Schizophrenic children, respectively. So we've got parameters down. Well, we use these parameters now to define the hypotheses. So here's our mu1, mu2. Let's test H naught. In H naught, we have something that goes like this: mu1, mu2. We put a symbol in the middle on this one that will say against. The alternative hypothesis. This alternative hypothesis would capture the research question if they had posed it directly. They didn't, so it has to capture our practical question that we ourselves stated to direct our analysis. So whatever we stated here has to be compatible with whatever the alternative hypothesis is going to be. So let's go mu1, mu2, put something in the middle like before, using alpha equals something. Now, if we go with a 0.05, we have a 5% chance of making a type 1 error, and we have to judge that against what a type 2 error would be. But in this kind of setting, dealing with human psychology, it's really easy to be afflicted by lots of type 1 errors when we don't necessarily publish the studies that fail to show statistical significance. This is actually a bit of a problem in some of the research journals in this area of the sciences. So what I would do if we're dealing with human psychology personally, and we're potentially going to make a big statement about people in a class of ordinary diagnosis versus a schizophrenic diagnosis, I would never want to make a conclusion that would be false. So I would probably set for alpha personally on this one to something very low, a 0.01. I would want a huge amount of evidence before I make any statement about human psychology right over here. That's just a personal choice. If you went with 0.5 or even a 0.10, I would just think you're balancing the type 1 error, type 2 error, and that problem in a different kind of way. But we haven't even filled out the hypotheses entirely. Anyone see what should go right here by the red dot? Should this be less, greater, or not equals? Good call. If there is no research question or direction on how to analyze, we go by the default test, absolutely, the two-tailed test. You would have to have something in the context that would say use a left tail test, less than sign. Something would have to direct you to a right tail test. We can't use our personal feelings about the data. You have to use what the author told us right here. So missing any particular direction, it's a two-tailed test. We must use not equals on this problem, which means over here, we take the negation of that and we call them equal. So our author will always put equality here, but if he went greater than, you might have went less than or equals, which is totally fine, like we mentioned. And if you went less than, it would have been a mistake here, but if you went less than, go greater than or equals here, and that would be correct as well. So we have the plan. We have the parameters down. We have the research question that we supplied ourselves. And this is the formal statement of the hypotheses. Any questions at all, folks, before we take a look at the conditions next? Okay, takes a bit of work and thinking about the problem just to get here. Our ultimate goal is to give a strong conclusion down the bottom. So this is all just the initial thoughts to support that conclusion. So next thing we do is, first, take a look at the data. Because it was independent, we need to analyze these data as independent columns. It would never make sense to form the pairwise differences. Like we mentioned, these two children have nothing to do with each other. Subtracting those values is not going to give us the right analysis at all. So back in RStudio, let's import the data set. Mine is on a thumb drive in this folder for chapter 18. Same exact folder on the Moodle website. I'll just leave it generically called example 4. We have the normal children, the schizophrenic children. Let me close out that tab, and here's our data imported. 20 observations on 2 variables is what we expect to see based on the write-up. And on this problem, I think what's kind of convenient is to just extract these variables separately from the data frame. So I want to go and write ordinary gets example 4, select with the $sign, the normal children, and then I'll just shorten the next description to skits for schizophrenia, gets example 4 again, $sign, hit enter on schizophrenic so that we don't have to worry about misspelling that. And now we've got our data imported. Let's hit Control A just to make sure it came in correctly. It says 20 values on both. Looks like we're in the right step. So let's say for here, this part we're going to deal with is condition checking. And because we have to give a display for both of these variables, you could do the histograms individually, but it's kind of inconvenient. You could just, in RStudio itself, control the graphics so it gives side-by-side displays. I don't think we've done that before, so this would be new syntax. Let's comment this out in case you decide to use it. What you would start with is par, graphical parameters, mf row. I need to do some research. I personally don't know what that does. I just know it works. We set it equal to C, 1, 2, to say I want 1 row, 2 columns. But any vector here you like, you could go 10, well, I guess that's 19, 20. Now you have 19 rows, 20 columns. Certainly we're not putting out that many graphics, but you could if you needed to. And it formats it pretty nicely. After you do that, let's just run a couple histograms. Do hist for ordinary. We'll clean these up, but we just want to check if this is even working in the first place. Hist again for skits. And then if we end it right here, your graphic behavior is always going to stay the same. So we want to reset the way the graphics work by setting this back to C11. So call par again, MF row equals C11. And this resets the behavior back to normal. So this is side by side displays. This is resetting display back to the ordinary setting. If it all works, let's test this out to see if we're close. Hit Control A, Control Enter, and there they are. We have 2 side-by-side displays now. Well, any questions, folks, to this stage? Okay, lots to still do to clean this up a little bit. So let's do that here just as the last things. First thing I usually do is delete the main title. That are way too long, and we already know we're looking at a histogram, but that is just a personal choice. If you'd rather have them on there, you just would want to change it to a more reasonable title, I'd say. For me, I usually go like this. The main title has been deleted. Hit enter just so we can fit this all in one line or one screen without scrolling horizontally. XLab refers to the X label. So instead of just saying ordinary, we should be descriptive. These values along this scale is for the TAT. I want to say TAT test, but that's redundant, it turns out. So we should say TAT score for ordinary children and just hope it fits. We'll see if we can make it fit at the end and then revise this if we have to. Then just redo all that for the next group. Main title's deleted. X label is going to be TAT score for, now I have to spell this carefully, schizophrenic children. We'll just go with that. Let me know if it looks oddly spelled. And now that would be the end of all the condition checking. Okay, let's see how this cleans up. Looks really bad now that we reran it, but again, we have this squeezed down to a small spot. So click the export button, copy to clipboard. Here's where we're going to see if we have to change our titles. We should be able to resize this nicely though. Yeah, that looks like it's pretty decent set of side-by-side displays. So I'll take a screenshot, but with metafile selected, you can hit copy plot right here as well for the same effect. And this would be the displays I would use to support the hard part of this analysis, condition checking. So that's where we're at on the solve part. In condition checking, we have to include a display to support our conclusions. And there it is. If this just feels like it's taking up too much screen real estate, feel free to resize it however you'd like. And as far as the condition checking goes, if we were dealing with this sort of data back in chapter 17, in fact, we did deal with that kind of data, that was not good. Sample size 19, not too different from us, sample size 20, except the condition checking on this was for one sample t-test. We have 2 samples, and we leverage both sample size 20 here and sample size 20 here together for a total sample size. So let's start by saying N1 plus N2 is 20 plus 20 equals 40. And now start counting the things that are working in our favor, actually. We have that there are equal sample sizes. That's very important to already for one bit right here. We scroll down and look at the conditions on robustness. One of the major things that helps us out is equal sample sizes in both groups. So seeing that is a great help. If it looked like, say, 20 and 17, that's still pretty dang good. So being off by a little bit is not problematic. If it was, say, 20 and 7, that's not as good. That's starting to hurt robustness. The sample sizes are becoming markedly unequal at that point. But 20 and 20 or 20 and 23, anything like that is great for robustness. Now, it's not great that they're skewed, both of them. This one seems to have a bigger potential outlier right over here in the schizophrenic group versus over here in the ordinary group, but they both seem to have an outlier on the upper end. Both skew to the right, but it's actually a plus for us that they have similar shapes. We can say next, both distributions are skewed right, having similar shapes now. That's humongous for robustness on the two sample t-test. In fact, that's the first thing that our author really wants to discuss when he's talking about robustness. It's a more robust test, the two sample t-test, and the extra robustness is improved when there are similar shapes. So just because it's skewed is not necessarily bad. It's helpful that they're both skewed in the same exact direction. If one was skewed left, one was skewed right, they do not have similar shapes, and that is actually pretty terrible. We would want a higher sample size over here if we had different directions of skew. So what else do we have going for us? Well, let's see. Equal sample sizes, similar shapes. Let's see. And our sample size, we analyzed, is in this range. I mean, it barely made it, right? It's at the cross or the boundary right at 40. But at large samples, the T procedures can be used even for clear skew distributions when they are large. We could even overcome presence of outliers as well, even though our author didn't directly say that. Sample size 40 gives us even more protection against outliers. Let's see how bad those outliers are so we can give a final conclusion. If this is significantly far away, if we view it from a different plot, say a box plot, we might feel that this is not great looking data, but I think our sample size would be large enough to overcome the size of this outlier right here. Let's add one extra display just to get a better view of this. Since we are thinking about outliers next, we want to take a look into some box plots. So we're not done with condition checking. Let's now go box plot. Let's see, there's a different way to kind of do this, but let's just do it the same way we did over here so we don't get too crazy with our analysis. Let's go box plot ordinary, box plot skits. We'll clean this up, but first we'll run it. And let's see here. I want to take that, drop that line here. That makes a little bit more sense. I think everyone would agree. So that when we go do the box plots themselves are on a side-by-side display. Not a big deal, right? You can click the left arrow to see the other one, right arrow to get back to the other one. But this one line just makes life a little bit easier. It's not a bad thing to bake in. So try it again. And they're both here. That outlier does look like it's a bit more concerning than I would like. So these data are starting to look a little bit more borderline on the conditions. Other things we have to do if we're going to add this to our plot is, well, now we need to say, what are the axes? So let's go to ordinary, give it YLab label equals TAT score. And for X label, let's see here, which one did we plot? This is for ordinary children. Let's just write in ordinary children. Let's see if that fixes it in a satisfying way. Yeah, that'll work. I wish I could find a way to make that a little bit higher, but with using basic packages in RStudio, this will do the job for us. We don't have to get too fancy. Unless you're going to use this for a living, you'd start installing extra packages to get a little bit more control on your graphics. Let's do the same. YLab equals TAT score. XLab equals schizophrenic children. So now we have our displays filled out. Click copy to clipboard. Resize as necessary. Let's see here. Uh-oh, let me try again. Resize as necessary. That should do the job. And let's bring this in. Now, analysis looked pretty good right here, but we were concerned about that one. And now that we're looking at it under this display, you might be like me. I would be more concerned now. It's pretty far away from their main grouping of data. That looks like it would be considered a pretty influential outlier. So let's mention this here. The group of schizophrenic children contains a highly influential outlier. To me, that looks like it's the first big concern with the two-sample t-test. These data are really pretty borderline, in fact. I think a lot of people would argue whether the two-sample t-test makes it or doesn't, and these would be very spirited discussions. There's a lot to add here. So what we're going to do is we have to make a decision. We'll make an assessment, and then we'll mention what the non-parametric procedure would be for those curious to run the non-parametric analysis. In your view, the two-sample t-test conditions are not met because of that outlier, that would be the right analysis to make. But you're always welcome to use the ordinary two-sample t analysis and just mention your conclusion, what the shortcomings might be, like we have done in the past. So at this point, here's what I would say. Since the total sample size is 40, the conditions are met except for the outlier. So we have a problem right there on our conditions for robustness. And I think if you look into the problem again, nothing in the problem said how they collected the data. Let's see. Yeah, they just said, ask 20 mothers of these children, 20 mothers of the other children to complete the TAT score, never saying how those children were actually put into the study. This was published in the Journal of Abnormal Psychology in 1970. So we hope because it was published, there really was randomization there. But for us as outsiders looking in, that's another unknown, and we should mention it. It is not clear if these data are random. So let's give the analysis for the two-sample t-test. Then, just like in chapter 17, we'll show how the alternate analysis could go if you're curious, and if you encounter a problem where you feel it just doesn't make the cut, and you would prefer not to run the analysis and just mention the shortcomings. So this is the fun part of RStudio, I'd say. Condition checking is tough. But now when we go back to actually doing the computation of the test, here's what it looks like. So we're at the end of condition checking. Let me just kind of put these a little bit more together. And now here is the two-sample t-test not, this is a good thing to clarify, not assuming equal variances, like we mentioned before. So we totally just ignore that. That's not a required assumption for the test we're running, the Welsh two-sample t-test. Call t-dot test, include ordinary children as the first input, schizophrenic children as the second input. And notice this is the exact way we worked with t-dot test in chapter 17, except that there's just an extra column to accommodate for the extra variable since we have two independent samples. That's really right there, the only difference. Now, before we get too far, let's take a look at what our hypotheses are. That's a two-tailed test. So let's go to alternative equals. It should be set to two dots cited with quotes in order to do the right analysis. These are for the right tail test and the left tail test. So go alternative equals two dot cited. Then we have to look at another element of our hypotheses. We used a high benchmark for evidence to reject the null. Significance level is at 0.01. That means the way we control this in our studio is we go to the confidence level and do the following. Go conf.level equals, put in 0.99. Let's add a comment. Confidence always equals 1 minus alpha, where that alpha is the significance level set to the 0.01 right here. So that's why our confidence level is at a 0.99 down below. This should get us going. Let's run this, see what we get out of it. We have our analysis down below. When it says Welsh two-sample t-test, again, that means we're allowing for unequal variances in this problem. It is not a required assumption. This is quite a powerful and a fancy test because of that. Degrees of freedom is 36.708, never had to be an integer. I'm going to do an analysis where I just give the test statistic 2.662. So down below for the necessary computations, here is one of them, 2.662. What does that say about our hypotheses up here? It says the distance from U1 away from U2 is about 2.662 standard deviations. You know what? That's pretty far. But this is a two-tailed test, so that might not be good enough to meet our benchmark of evidence. Our p-value is that figure right there. So down below, so I fix my window, there we go. Let me write in p-value equals 0.01146. And that was just so I could keep that in my head as I wrote it down. You could do a screenshot as we mentioned before, pen it in, type it in. Your preferred method is going to be totally fine. As long as you convey the information, these are the two major things I'm looking for, test statistic and the p-value. Well, at this stage, we're ready for a practical interpretation. And this is just a reminder for me. Provide non-parametric analysis. I'm not too sure what I misspelled on that. Let me just make Google do the work. There we go. So to give a good conclusion to this, what we now do is we go to the very top. Once again, sorry for all this scrolling. Grab this information, what you said that your parameters were defined to be and what you defined your hypotheses to be. Critically also include your significance level alpha. This is a good idea to put it in line with your hypotheses. So a place where you would check a lot of stuff quite often. So now next thought. P-values at 0.01146. Significance level alpha, I set personally at 0.01. This is greater than 0.01 equals alpha. We didn't meet the benchmark of evidence in this problem. So that means we fail to conclude HA is true. In other words, we don't have a conclusion the null hypothesis is true. It's still off the table. We still give a conclusion targeting this, but we just say our level of evidence found in the problem wasn't enough for assuming this is true. Let's write it out by saying this study does not provide significant statistical evidence. And I want to put a parenthetical in here that we haven't done as a class very often, but it's something that you might want to do as part of just conveying this was a high benchmark of evidence. I'll put here at the 1% significance level. It's in parentheses because if we're giving a practical interpretation and you told this to someone, they might follow up by asking you, what does a 1% significance level actually mean? And that's like a 90-minute digression into all the statistical nuts and bolts to get there. So it doesn't quite feel like a practical interpretation when we put it in, but it's kind of like saying with 95% confidence if we're doing a confidence interval. It's just saying the level of rigor in our estimate or the benchmark for evidence that we had to cross in order to assume that this is true. So you don't have to put it in, but if you feel like it's a worthy statement to throw in, not a bad idea. So at the 1% significance level, we did not provide enough significant statistical evidence to conclude ordinary and schizophrenic children have different TAT scores on average. So don't forget the fact that we're talking about mu1, mu2, so we have to say average somewhere. Another way you might have read out this sentence starting at the red dot is you might have said we don't have significant statistical evidence that the population mean TAT score for ordinary children is different from the population mean TAT score of schizophrenic children. I said it in a totally different way. As long as you have average in there, you've got the right same equivalent type of expression. So this is surprising in a way, because if you look at these data, I think a lot of people would be captivated in thinking these numbers are way lower than these numbers. That's not really true. That's not what our statistical analysis is even saying in the first place. These are actually close, and that's kind of a strange conclusion to come to. They're close, and we used, well, a high benchmark for evidence and a two-tailed test. They were not different enough to really see the statistical significance. Another thing that's really dangerous about this problem that we've kind of hinted at all along is we can't insert our own assumptions about the data, about the populations whatsoever either. If you did a left-tailed test on this one or a right-tailed test, we could have lost some credit on this one because by its nature, we were investigating any difference whatsoever. So a really, really strange problem. This is our conclusion, but that conclusion could be massively challenged. So let's mention some shortcomings. This conclusion can be challenged on the basis that the sample size N1 plus N2 equals 40. Just a reminder, we're thinking the total sample size on condition checking is not large enough to overcome the outliers. That's kind of unfortunate in a certain sense, But there's lots of things you could do. We could provide a non-parametric analysis, or if people want to stick to the two-sample t-test, sometimes they want to look into how influential were the outliers really. Remove them, run the test again, and look at that analysis. But be very mindful when you do that. It's just to see how these values change if you did remove them. It's not the official analysis. It's just a check on how pivotal were those outliers as well. So even if you do remove them, these are the official test statistic and p-values even still in our analysis. If this p-value, say, dropped a little bit when I removed the outliers, I would feel like we were on the right track with our conclusion. If the p-value increases when we drop the outliers, well, we might have a different kind of problem with that. Well, hang on, I think I said that backwards. Let me try this again. If it increases when we remove the outliers, it'll be even bigger than alpha. That means our conclusion was in the right direction if it increased upon removing outliers. That's, I think, what I should say. Delete that prior statement. But if we delete outliers, and this actually goes down, that would change our conclusion, and now it would tell us we have a bigger problem than we really thought. We really must use a non-parametric analysis in that case. Well, I'm not going to ask you to do that kind of what-if analysis, but it's encouraging to know that there's a lot of different tools in our toolkit. As an introductory class, we're going to look into the primary tool of a non-parametric analysis. So that's what was my reminder. I'll put here, provide a non-parametric analysis if you decide that the two-sample t-test conditions were violated so badly that the test should not be used at all. So that's what we're going to look into next. So the non-parametric test is going to be called, let's see here, these have some weird names. I believe this is the Mann-Whitney test. I wrote down use Wilcox dot test. That is the same structure that we used in chapter 17 for our non-parametric test. So just like t dot test handles one sample, t dot test also handles two independent samples. Same with Wilcox dot test. But there is a real big downside with non-parametric analysis. Here's the downside. Your null hypothesis goes this way, H naught. Both samples come from a distribution with, I want to say, the same center, shape, and spread. This is taking us to really chapter 1 of the course. Shape is going to be whether it's symmetric, skewed left, skewed right. Center is going to be the central value, possibly measured by the median or the sample mean. Spread is how it varies, possibly measured by interquartile range or standard deviation. But if we're using non-parametric test, spread, we're probably thinking interquartile range, and center, we're thinking median. Except it's a complicated test. It's not even the median exactly that's being measured. Here's the next thing. Alternative hypothesis will say the samples came from distributions with different centers or different shapes or different spreads. Now, if this is a nasty kind of OR, this is an inclusive OR, What that means, at least one condition is true, or maybe exactly two conditions are true, any pair of conditions, or perhaps all three are true simultaneously. But what we care about is different centers. That is an analogous thing to say the sample means are different, but it could have been the centers are the same and it just had different shapes. It's not the conclusion we want at all. It's a kind of a nasty non-parametric test where the alternative has things that we don't actually want. Let's think about different shapes though. Looking at the sample data, we have good evidence that the populations have similar shapes because we see it in the sample data itself. So if we reject the null hypothesis, assume the alternative is true, it's probably not that we're assuming the shapes are different. What about the spreads? If the standard deviations are pretty common, we might assume that we are accepting the alternative hypothesis, not because of the spreads, but because of the different centers, that's the real major issue on why the null was rejected and the alternative was accepted. So we hope to show that this is the major part of our alternative, but when we give a conclusion, we have to say the whole thing. That's the conclusion to the test. So that's a really weird kind of alternative hypothesis. Let's mention here, we hope to show this is true. So let's run the analysis and see what we can conclude out of here. Any questions first, folks, with a quick discussion on this new non-parametric test? Okay, let's jump in. Take a look at how this one should go. So this is starting to get kind of long. I'm definitely going to share all of it. Now at the very bottom, let's say here, the non-parametric approach goes like this. So call Wilcox.test, also known as the Mann-Whitney test, is what they're referring to over here. Just like what you did on T.test, pass to it the variables, ordinary, skits. We need the same exact alternative, so we should write that in. Let me think about that. I don't think we pass to it a different specific alternative. I believe this one is set as a default. There is no notion of a left tail versus right tail test on this one. What we should pass to it is the confidence level. Well, yeah, let's give that a try. Dot level. Second option, 0.99. And this should do the job for us on our run. Okay, so hit Control A, Control Enter. And the first warning is same kind of warning that we got from before. Cannot compute exact p-value of ties. What it's letting us know is this is an approximation now this time. So that's not a big warning. It's not telling us our analysis is wrong. The alternative hypothesis is that the true shift in location is not equal to 0. That's talking about different centers, but you really have to do the analysis on, was it different shapes? Probably not. Ours look similar. Or was it different spreads? Those are also actually included as well. So maybe the next thing we should look into, one last bit, the syntax, analyzing the spreads. Let's look at standard deviation for ordinary children, standard deviation for schizophrenic children, and just see how they compare. Those are pretty common standard deviations, or pretty close, I mean, rather. I don't have a really good rule of thumb for that, but if one was double the other, I would say that the spreads are very, very different. These are now pretty close. So now, and looking at our analysis down here, I would agree with RStudio. This looks like the right conclusion to make. True location shift not equal to 0, meaning we really have different centers. We are kind of putting into the corner in the alternative hypothesis, this is the major conclusion we want. We're not going to conclude on different shapes. We saw already in our analysis the shapes are similar. Different spreads, they didn't look too different when we looked in our analysis. Looks like it was really the different centers. So we would grab, let's do a screenshot on this one. Here's the analysis, and our conclusion would be, we can conclude that the ordinary children and that's again a tough word for me, schizophrenic children came from distributions with different centers. How did I get to that conclusion? Well, I did make a mistake on my hypotheses. I stated the null, the alternative. I should have stated the significance level alpha, right? That's a big omission. What it should have been, though, is the same exact significance level alpha for the original test we intended to run. We cannot change that whatsoever. So we baked that into our syntax when we ran this. And now this is less than 0.01 equals alpha. It's now significant, which means it might question our analysis up here where we decided it was not significant. Again, these set of data are not easy to analyze, and that was the intention, to show some very, very borderline data where you could have a very good debate on which way the conclusion should really go. This non-parametric test says there might actually be a difference, and it's significant at a high level of evidence. But what it doesn't provide for us is a confidence interval. You have to work really, really exceptionally hard to get to now a confidence interval to show the nature of that difference, to show how big and impactful it is. But thankfully, for our part B, we're going to give a confidence interval for the two-sample t-test instead to end our analysis. So think of the Wilcox-Rinck sum test that we just ran, or the Mann-Whitney test, as just a different way you are allowed to go on your statistical analysis if you believe the two-sample t-test is just too badly violated to really use. Any last questions at all, folks, running this analysis? Okay, last thing to do, let's grab all of that, put it down below, and this is how we analyzed our data. We had a lot to do on this one, but again, it was intentionally a problem that had some challenges, so we can just see what all can go wrong with ordinary data like we just dealt with. Last part is just a reminder, even if everything went right with our ordinary test way up here, this is not the end-all be-all when you do a statistical analysis. This is the initial analysis. We ran a test of hypotheses and we detected, well, no difference. But we still want to follow the analysis. Even though we don't have a conclusion of a difference on this hypothesis test, we still want to see what is the estimate of the difference between mu1 minus mu2. So that's going to be our next analysis. Let's take this down just to make it available as we give our conclusions. Next, go back to RStudio. And in our things that we ran the Welsh two-sample t-test. Our confidence interval is right here. We just have to interpret it and analyze it. Let's screenshot this thing out of here. Okay, so we had the confidence interval all along. This interval tells us that mu1 minus mu2. Notice the order that I subtracted these. It has to be the same exact order that you indicated them in the null and in the alternative. Always try to keep everything directly the same, because now suddenly when you're going to the confidence interval, that order is very, very specific. So this will be greater than the lower bound, negative 0.02. I was going to try to put a unit in there. That's not going to fit. Up to the upper bound, let's go with better rounding, negative 0.03 on that one. And then less than 2.93 on this one with a unit of points. So this is why we did not reject the null hypothesis. In a 99% confidence interval, 0 is included here, which means mu1 minus mu2 can in fact take the value 0, no difference. That loses our statistical significance in the hypothesis test, but this is still an interesting estimate in its own right, so let's interpret it as well. So we can interpret it by doing a little bit of extra algebra on it if we prefer, or just leave it right in this format. Let's leave it in this format and do an interpretation that goes like this. Let's see here. Children who, geez, this is a hard sentence to start. I'm thinking mu1 when I'm starting this sentence. So let me just follow this structure and say the population mean TAT score for ordinary children so we're talking about mu1 here. When we subtract mu2, it's from this range to this range. So we can say is from 0.03 points below, the below is capturing the negative sign, to 2.93 points above capturing the positive number. Now it's referred to mu2, the TAT score for schizophrenic children. And I did forget one thing, but the good news is you can put this at the start of the statement or at the end. We should always mention the confidence level. So I'll say with 99% confidence. So that does it for us, folks. This is the follow-up analysis. We subtract mu2 and we get a positive number. Well, that means mu1 was about 2.93 points above the second parameter. And if we get a negative number, it means it was 0.3 points below the second parameter. So we referred to mu1 when we said mean TAT score for ordinary children. And we referred to mu2 when we said, the mean TAT score, missed a word there. Let's include that. The mean TAT score for schizophrenic children. And we got the confidence level in there as well. So that would be the follow-up analysis. When you're running a hypothesis test, even if you fail to reject the null hypothesis, this is interesting information. People still want to know about it. That's why RStudio spits it out whether you ask for it or not. It's part of the overall analysis altogether. But textbook problems are weird. Oftentimes we just do the part A, a hypothesis test, or just the part B, the confidence interval. This last problem was also a reminder, these really do go together in most analyses. Well, that's the end of chapter 18, folks. You made it. Congratulations on getting through this one. Next chapter is a lot nicer. This one is kind of sketchy with the extra things with two independent samples. But any last questions or comments at all with this one before we take a look into the next? Okay, we've got 9 minutes, so I'll make sure not to run over time. Let's find a really good stopping point. but also take a look at what we're getting into. So we're now dealing with categorical data. You'll notice we haven't talked about categorical data a lot, mostly in chapter 1, it seems like. So this is a welcome change of pace. Categorical data is just as important as quantitative data. The way we analyze it feels very different. There's some commonalities though. Here's the central limit theorem for quantitative data. It's a sampling distribution of X bar. But we're converting over to categorical data. P hat is a sample proportion of successes or sample percentage of successes. And we need a new central limit theorem to represent the new statistic. Here's that new central limit theorem for the population proportion of P successes. The statistic P hat is distributed in this way. What we do with this is, first we'll run a problem where it uses a central limit theorem in an honest way. It's rude to state a theorem and not do a problem on it. But the major thing we want with this central limit theorem is change right here. We come down below, and we're going to compute the standard error of that part right there. Notice that's exactly, I mean really dead on exact what we did for our chapter 17 problems when it was quantitative data, one mean. Once you have a standard error for there, the confidence interval is going to be the estimate, P hat. Add or subtract the critical number. Notice Z star makes it come back, so that's a welcome addition. Multiply by the standard error, but the standard error looks essentially the same. Only change we make is P hat goes inside right here instead of P. So that's our whole process. Once we get that standard error in there, everything works as normally. Well, except that it's categorical data. That's something that's not going away. But the hypothesis tests go in the same exact kind of way. What we do is we calculate a test statistic, measure the difference between the data, P hat, that's the statistic, and the null hypothesis assumption, P naught, is the value to be tested. This is going to give us a number of standard deviations. P hat is away from P naught. And then we analyze the P value in same exact way. So there's a lot of redundancy or carryover in the logic we've been using all along. The hard thing about these notes in chapter 19 is really just getting started. So let's maybe do, let's see, we've got 7 minutes. Let's try out the getting started problem just to see how all this goes. So here's the old central limit theorem. It's just here to convey, we need to change this around to a new one. And here's how we're going to start. We gather a random sample of size n, but we take n recordings of a categorical variable, and critically, it only has 2 categories. That seems restrictive, but we'll get into chi-square procedures, which will allow for 3, 4, 5, and so on categories. Because there's 2 categories, we'll denote them by a success or a failure. That's our dichotomy. The success is going to be the thing that we're interested in the most. The part of the study we are interested in. So that'll be the success in the sample. Then we get a new random variable. This one I'm calling discrete, as opposed to a random variable from a normal distribution would be a continuous random variable. This one is discrete because it just counts the number of successes in your sample directly and a sample size of n. And notice where x goes. It goes into the numerator of something. It goes into the numerator of P hat, the sample proportion of successes. This is the statistic now. We throw that in, the successes in the sample, and now this is just a percentage. Add the sample size n, what percent designated is designated as a success. It's written as a decimal, but change unit, and it's a percentage as well. So P hat is the statistic. The unknown parameter is P. And just to kind of compare things, prior, say, chapter 17 or chapter 18, X bar is the statistic. And in chapter 17 or chapter 18 with 2 parameters, mu is the parameter. So this is the hardest part again about chapter 19. We have to get used to p hat playing the same exact role as x bar, the sample mean. This is just the sample's proportion of successes. And we also have to get used to p itself without that little hat right on top, just a p with no decoration whatsoever. That's the parameter, and it plays the same role as mu. So we use the parameter p for categorical data, which means we're using p hat as a statistic. And we use the parameter mu for quantitative data. Again, it's kind of interesting to see. This is the role that chapter 1 played, but it's been a long time since we talked about the two different kind of data types. After putting that all together, we can now investigate problems like these, finding the statistic parameter. Then, this is the bigger problem. Think of example 1 as a warm-up, but example 2 is a direct use of the central limit theorem. We'll have to carefully think about what is the statistic, what is the parameter, in a study that hasn't even collected the data at all in the first place, just like we looked into on chapter 13. So felt like we might be able to do example 1, but this is important enough work to really think strongly about the differences between the statistic and the parameter, the new one, p hat and p. I think it might be a good idea to come back on Thursday fresh and take a look at example 1. Does that sound all right to folks? Okay, when we come back on Thursday, we'll hit example 1, review this as needed to support getting through this problem. Then we'll be on our way doing a couple analyses, probably a couple conference intervals. Likely we'll finish these notes a week away from today and then move into the chapter 20 type problems. Well, we'll call it a day here. So if you have any questions, I'll be happy to help out. Otherwise, have a great afternoon, folks. I'll see you all next time. And before I forget, let me get one of these back.